In the next couple of videos, I'm going to illustrate how to carry out a one-way MANOVA where you have an independent variable with more than two levels. So for the example that I'm going to provide, it will have actually three levels of the independent variable. Keep in mind with MANOVA, you are basically assuming that your independent variables are categorical and your dependent variables are continuous. So your independent variable can be a nominal scaled variable, an ordinal scaled variable, or a discrete ratio scaled variable. That's basically a count variable. So at any rate, here is the example that I'm going to utilize. Let's say I'm a researcher studying high school students concerning their plans for further schooling after graduating high school. I collect data on 52 individuals on 4 variables. Plans regarding further schooling, academic self-efficacy, perceived utility of college for achieving future goals, and intrinsic motivation for learning. So the variables in my data set will include plan, which is a categorical variable, coded 1, plan not to go to college full-time, 2, plan to go to college full-time, part-time, and 3, plan not to go to college at all. The second variable is self-efficacy or academic self-efficacy. It's assumed to be continuous, where higher scores reflect greater self-efficacy. The third variable is perceived utility, which is assumed also to be a continuous measure with higher scores reflecting greater perceived utility of college. And then number 4, it is intrinsic motivation. It's also assumed to be continuous, where higher scores reflect greater intrinsic motivation for learning. So basically the independent variables plan and self-efficacy, utility, and intrinsic motivation are my 3 dependent variables. And so in the video I'm going to illustrate several possible follow-up tests. One is univariate ANOVAs that might be followed by either post hoc tests to explore possible univariate mean differences or the use of plan contrast. There's also step-down analysis, which addresses some of the problems associated with the univariate ANOVA strategy, and then also discriminant analysis, which also addresses some of the univariate ANOVA strategy. So here is my data set in SPSS. I've got my variables plan, there's my categorical variable, independent variable, self-efficacy, perceived utility, and intrinsic motivation, my 3 continuous dependent measures. So I'm going to go ahead and run the MANOVA, and I'm going to just use the post hoc tests for the time being to illustrate that particular strategy as a follow-up to the MANOVA. So I go to Analyze, General Linear Model, and then down to Multivariate. I'm going to put my independent variable into the Fixed Factors box and my 3 dependent variables into the dependent box. Under Options, I will select these options right here so that I get my grand mean as well as the group means. Descriptives, effect size, power, and homogeneity variance, homogeneity variance covariance matrix, C's assumption. Click on Continue. Under post hocs, if I want to explore univariate mean differences, I can move this variable over to the post hocs box, and then I can click on 2 keys to explore univariate mean differences. I can also ask for plots. If I move the independent variable to the horizontal axis and click Add, now I'll get profile plots for each of the dependent variables. So if I click on OK, this is my output. So as you can see, we've got all of this information right here. These are the descriptives. You have your means for each of your groups for each of your 3 variables. So you can see that on academic self-efficacy, really there were no real differences between those who were attending college or plan to attend college full-time and plan to attend part-time. But there was a difference, descriptively speaking, with those who plan not to attend, with those individuals scoring lowest on academic self-efficacy. On perceived utility, you had sort of a similar trend where the lowest mean was for those who plan not to attend college. And then for intrinsic motivation, similarly, you had the lowest mean for individuals who plan not to attend college. The highest mean was for those who plan to attend full-time versus those who attend part-time. So those are the descriptives for our three variables and for our three groups. Now we can look at the MANOVA results, and so you have your MANOVA summary table right here, and here is your independent variable. And so you'll notice that in the two-group MANOVA case, basically all of this information right here from the F on over, all that would be equivalent. And that was really because there was only one discriminant function that was being used to compare the groups on. So in the case of, in the case of where you have more than two groups, what we have is more than a single discriminant function, which is mathematically how the groups are being separated. So each of these tests then capture a different, provide sort of a different lens for talking about group differences on the set of dependent variables. So quite often folks report on Wilks Lambda when they were comparing groups. But keep in mind that actually Roy's largest root is probably one of the more powerful ones, because it focuses in on the first discriminant function, which is actually the function that the groups are most likely to be separated on. Whereas Wilks Lambda sort of takes the entire ball of wax into consideration. So at any rate, kind of looking at our multivariate results, I'm just going to focus in on Wilks Lambda here. And so for this particular row, you can see that what this is telling us is that we have significant group differences on the set of dependent variables. Between the basically between the plan groups. So you can see right here we have our p-value. So this is p. And you can see that is less than our alpha threshold. I think we just set it at 0.05. So this would tell us that we have significant group differences on the set of dependent variables. We also have partial eta squared, which again is our index of effect size. If we utilize this in relation to Cohen standards for judging the effect size for the social and behavioral sciences, this would be considered large. Keep in mind Cohen's conventions are eta square values of 0.01 would be considered small effect, 0.06 or thereabouts would be considered medium, and values around 0.14 or greater would be considered large. So this is clearly a large effect of plan on the set of dependent variables. You can also see we have the power of the test. This is just indicating the likelihood of correct rejection of the null hypothesis, and so essentially it was 100% in our data. And so this is actually the observed power is calculated after the data are collected, as opposed to an a priori power analysis where it's collected before. The other thing to note is we have the assumption of homogeneity of variance covariance matrices. Basically, a variance covariance matrix has variances in the primary diagonal of the matrix and covariances on the off diagonal. And so what we're basically testing with Box's test is whether the elements in the variance covariance matrices across our three groups, whether those elements are equal or reasonably so. So in this particular case, what we're looking for is a p-value that is greater than, say, 0.05. And so in this case, it actually was the case. So that would allow, so we could infer that our assumption is met. Now keep in mind the downside, and so why do we care? Because this the assumption of equality of covariance matrices is a precondition for the interpretation of our multivariate tests. And if our assumption is not met, then it calls into question our multivariate results. A violation of this assumption could lead to an increase in type 1 or type 2 error, just kind of depending on the nature of the violation. At any rate, it appears that our assumption is met, at least by virtue of this statistical test. So we would infer that basically we can our results are reasonably trustworthy. Keep in mind that Box's test is only one way of assessing this assumption, and it can be underpowered in a case where you have low ends, meaning that you could have more substantial violations of this assumption if you have lower ends case, and so you may not be able to reject the null when perhaps you should be. On the other hand, if you have a high ends case, then you could actually end up being overpowered and rejecting the null hypothesis and concluding that the assumption is not met when there are fairly small departures from this this condition. So just keep in mind that any kind of statistical test of the assumptions related to your analyses are impacted by sample size, which impacts the power of those tests. So you just want to keep that in mind. So now let's scroll down a bit, and we have the univariate analysis of variances here. So you see you've got your independent variable plan, and you've got significance tests associated with each dependent variable. So in other words, there's a comparison between groups, between your plan groups or among your plan groups on each dependent variable. So the first analysis of variance involves comparing the three plan groups on academic self-efficacy. And you can see over here, you can see here's your F value and your P value associated with that test, and you can see that the univariate ANOVA basically indicates that there are significant mean differences on academic self-efficacy across the three groups. You can also see that there's pretty substantial effect size that's presented. For perceived utility, we see here also a significant mean differences among the groups on perceived utility. Once again, you have a pretty substantial effect size. And then for intrinsic motivation, what you see right here, here's your F value, here's your significance level. If we adopt an alpha at 0.05 criterion, you can see that there would be no significant differences among your groups. It's still a fairly moderate effect given the data. You know, keep in mind that when I'm using alpha at 0.05, I'm using it as a conventional standard. There are plenty of cases where you might increase or decrease alpha depending on circumstances related to your test, but the conventional threshold is 0.05, and so I'm maintaining that for these analyses. Note too that you have Levine's test of equality of error variances, and basically these are similar to the Box's test that we saw previously, except this is a comparison of the variances between groups for each dependent variable. So the variance on self-efficacy among the groups, you can see that the p-value is greater than 0.05. That would suggest that the assumption is met. So in other words, that gives us more confidence in the trustworthiness of this test right here. Perceived utility, we see that p-value is greater than 0.05, so that would also give us more confidence for this particular test here. And then intrinsic motivation, we have more confidence that we're not committing an error in inference for this particular test here. Now the downside of these particular tests, these ANOVA tests, is that they do not account for the intercorrelations among our dependent variables. So what can happen is that you can end up reanalyzing the same variation again and again by performing each of these comparisons. And that's the fundamental flaw associated with utilizing univariate ANOVAs as follow-up tests to the MANOVA. It basically violates the spirit of the MANOVA, which is, one of the reasons why we conduct it is because we would assume that there are intercorrelations among the dependent variables, and we don't want to analyze redundant variation over and over again. So that's one of the downsides of using univariate ANOVAs. Nevertheless, SPSS prints it out by default, and a lot of times people go with this this particular strategy, but it's not exactly in keeping with the logic of the MANOVA itself. So nevertheless, we'll just continue to scroll down, and you'll see now we've got our marginal means. Again, these are basically, the means are provided in the table above. You've got standard errors and confidence intervals associated with each group. You've got your means and standard errors for each of your plan groups as well. So for the post hoc tests, again, this is not exactly keeping with the logic of the MANOVA, but this is a common follow-up strategy that folks adopt, so I thought it was important to at least acknowledge it. So using Tukey's test right here, you can see that basically there are comparisons across the groups for each of the dependent variables. So there's academic self-efficacy, perceived utility, and intrinsic motivation. So you've got the I column here and the J column here. So in this column, you've got the mean difference, which is basically the mean for group I, which is in this column, minus the mean for group J, which is in this column. So you can see the difference between those who plan to go to college full-time and those who plan to attend part-time. You can see the difference is negative 0.785. So people who plan to attend college part-time actually scored about 0.785 points higher on average on academic self-efficacy than those who plan to attend full-time. Nevertheless, this comparison yielded no significant difference. So basically this difference is attributed to sampling error. When we compare those who plan to attend college full-time and those who plan not to attend college at all, you can see that those who plan to attend college full-time scored about 5.2 points higher on average on academic self-efficacy than those who plan to not to attend college full-time, or at all, excuse me. And this difference was significant. So we have a significant difference between this group and this group. Then when we compare those who plan to attend college part-time and those who plan to attend full-time, you can also see a significant difference between those groups, with those planning to attend part-time scoring higher on average than those who plan not to attend at all. And then basically these tests right here are just replays or redundant with the tests that I just went over with above. So for perceived utility, you had basically the same general trend. So there being a slightly, in this case, those who plan to attend college full-time had a slightly slightly higher mean on perceived utility than those who plan to attend part-time, but that difference was not significant, so it's basically attributed to sampling error. Whereas when we compare those who plan to attend full-time versus those who plan to not to attend, you can see that those who plan to attend full-time had a higher mean than the latter group, and this difference was statistically significant. Then when you compare those who plan to attend part-time and those who plan not to attend at all, you had the same general trend with the higher utility score or mean utility score being associated with the plan to attend part-time group. You can see on intrinsic motivation, similar trends kind of emerged. There were no differences between the plan to attend full-time group and the part-time group. There was also no significant difference between the plan to attend full-time group and the plan not to attend full-time, plan not to attend college at all. And you also had no significant difference between the plan to attend college part-time and those who plan not to attend at all. So, as you can see right here, really we had group differences, pairwise mean differences emerge for some of the group comparisons on self-efficacy and utility, but not intrinsic motivation. Okay, so let's scroll down just a little bit more and look at the rest of the output. You'll notice that here are the profile plots that come up, which is what we had requested. So you can see the means for the univariate means for each of our dependent variables. You can see this is that comparison. If you were kind of going back and looking at that Tukey's post hoc analysis, this was the non-significant difference here, but the differences between the plan to attend college full-time and plan to attend part-time, those comparisons with the plan not to attend, you can see that these are substantially different. Similarly, you had no real difference between these two groups here, but then the comparisons between each of these groups and the third group, plan not to attend, was also significant in the Tukeys. So you can see the general trends in the profile plots. And you saw similar trend here, but none of the pairwise mean differences were significant when kind of going back and looking at the Tukey's analysis. So if you're going to adopt this particular strategy of using Tukey's post hoc test, the basic idea is that you're following up the univariate ANOVAs and you're just trying to kind of explore where there might be some pairwise mean differences on the dependent variable. Another option is you can actually utilize, I'm going to just click off of Tukey's here. Another option is to carry out planned contrast. That's another possibility. If you want to, there are some canned options in SPSS. I am not a big fan of going through this route, to tell you the truth. If there was a situation where my independent variable was ordered and I wanted to compare and look at possible trend analyses or whatever, there are various options that are available, and one of them is a polynomial contrast option, which would allow you to actually perform a trend analysis. There are also other canned options as well, but I generally tend to prefer to utilize the syntax in order to specify a priori contrast. So if you specify your model and then you click on paste, then basically what you'll see is a syntax file that will come up, and you can modify this and generate certain planned contrasts. So for instance, let's say I want to compare groups 1 and group 1 and group 2, go to the plan to attend college full-time and plan to attend part-time on each of my dependent variables. I can actually, if you go to your syntax that was generated by virtue of clicking the paste menu option, what you can do is just use the L matrix command in order to carry out that comparison. So I'm going to type in \L matrix, and what I'll do next is I'll type in the name of the independent variable, which is plan. And so if I was comparing group 1 versus group 2 and not involving group 3 in any of the comparisons, then I would just say 1 and -1 and 0. So these are basically contrast coefficients, and they would need to sum to 0. So that would accomplish that particular issue. Let's say I wanted to carry out a more complex contrast. So let's say I wanted to compare L matrix. I wanted to compare the mean of groups, or the average of the means for groups 1 and 2, which is basically plan to attend college in some form or fashion, versus those who plan not to. So in this case, basically what I would do is I would say 1/2, 1/2, and -1. So this basically is going to instruct the program to take the average of the means for groups 1 and 2, which is the plan to attend college full and part-time, take the average of those means, and then compare it against the mean for group 3, which is plan not to attend at all. So if I highlight all this syntax and then click on the green button here, you'll see that you get everything that we had before, and you'll notice that now I have my different plan contrasts. So you can see right here, this is just basically the comparison between group 1 and group 2. So you have right here, basically you have the difference, or the mean difference, between the groups. And you have the significance levels. So these are p-values, and basically these are just t-tests. In other words, if you just take the difference, the mean difference, and divide it by a standard error, it would be each of these tests would be distributed as t, so basically they involve using the t distribution. So none of our our comparisons between group 1 and group 2 were statistically significant, and that's really not a big surprise given what we saw previously with the post hoc test. So these were all just simple plan contrasts involving each of our dependent variables. And so if we scroll down, you can see now we have our complex contrast, which was a comparison of the mean for group 1 and group 2 versus the mean for group 3. So here you can see that the difference in means, so the average of the means for groups 1 and 2 minus the mean for group 3, or that difference was 5.6. And that difference was statistically significant. So this is our p-value right here. The difference, so this is on self-efficacy. The difference between the average of the means on groups 1 and 2 versus the mean for group 3, the group that was not intending to go to college, that difference was 5.3, and that difference was also statistically significant. When again you take the average of the means for groups 1 and 2 versus the mean for group 3, you can see that the average of the two plan to go to college groups was higher on intrinsic motivation than the group that was planning not to attend college, and that difference was also statistically significant. So these are just basically univariate options as follow-ups to the MANOVA and now the analysis of variance. I just want to reiterate that the basic problem of doing all this, though, is again that it ignores the intercorrelations among the dependent variables. So by doing what we're kind of doing right here as a strategy, we end up kind of reanalyzing a lot of the same variation again and again. So in the next video, I'm going to discuss step-down analysis and discriminant analysis as two other options as follow-ups to the MANOVA.